That is Vitor from Brazil.
Hello, everyone, and welcome to the third session of the ME Academy on sedimentation modeling. The ME Academy is part of a series from the young water professionals of the Modeling and Integrated Assessment Specialist Group of the International Water Association. That was meant to be sharing knowledge with other young water professionals on the fundamentals of modeling. We have had 3 sessions. This is our third session. We've had a session on water models and how useful they are. And the second session was on activated sludge models. The session is on sedimentation modeling, and we will have continue doing these sessions throughout 2026 also. And without further ado, I'm going to let our speakers introduce themselves. I'm going to start with Imre, quick introduction, and then Elena.
All right, guys, I see a young professional, Dave Guinier, right there in the corner. Yeah, with his hydrogravity trap. Anyway, so, I am the head of Dynamita with the Sumo simulation program, and obviously I've been also involved with GPSX and BioWin quite a bit in this industry, about 45 years or so. So, but I'm still young, I think. So we'll look at this at settler models. Elena?
My name is Elena Torfs. I'm a professor at the Université Laval in Canada, and I've done my PhD now 10 years ago on settler modeling. So 4 years of sedimentation with Imre's PhD lying next to me on the desk. So I'm excited to share some of his background with you today.
Do you have another microphone, Elena? It's pretty muffled, isn't it? Or only for me? The sound was not very clear. Yeah, it's understandable, but it's muffled.
Is it better if I do it without headphones?
Yep,
I'll
better.
do that.
Okay, shall we run? Yep. All right. So I guess it's gonna be kind of a tech team. I will have a few slides, then Anna will have some more important slides, and then at the very end, I will also do a little demo on this flux model that we're discussing here. Maybe you can go to the next one, Elena. And then, so I just wanted, and one more, and I just wanted to, since I don't know how many people are very familiar with settlers here and final clarifier specifically, I just wanted to put up a photo. You can see sometimes the size is fairly large. You can see the little building next to it. And it could be shallow or deep clarifiers. Normally deep is better. And that you would be able to see on the next slide. And you see the person that's standing in there. You also see the structure. There is a traveling bridge that goes around. There is a center feed well, and so on. So this is kind of important to know what we're modeling. Phase separation in general involves a lot more than separating the liquid and the solid phases. Involves a lot more than these clarifiers. You can think about filters and membranes also. But today we're simply focusing on gravity settling. So going back to these are circular clarifiers, and I think the next slide will show a rectangular one. So in here, the idea is everywhere is to collect the solids that is settling down in the clarifier, and that in this case it's a traveling scraper that will collect the sludge into the hopper on the bottom, on the left side on the bottom. So if you look at this in the model, I think then you will see something very different. Let's see, choose on the next one. Thanks. Because essentially, we're dealing in this presentation and in maybe 80% or I don't know what percent, but in a big percentage of the sedimentation modeling, we're dealing with one-dimensional models. So that means that we have the vertical layers, but we don't deal with the with the horizontal distribution and density currents and all the other things. So the MLSS comes in a certain layer, and then we simulate what goes up and down, and Elena will explain this in more detail. And then if we go to the next one, then you will see that it could be even simulated even simpler. So in many packages, or the ones that I know, we also have just what we call point settler or volumeless separator that will simply split the mass. The mass flow that's coming into the clarifier is split into an effluent, which is usually, hopefully, the smaller or very small mass flow, and the rest has to go to the underflow. Then in some cases, we need to, so the point settler is not going to describe what's happening in the settler, and sometimes reactions do happen in settlers. For example, in primaries, there could be some fermentation, VFA generation, or in a final, maybe denitrification and rising sludge. So these can be better approximated in what we call a three-compartment settler. It has a center feed valve, the clear liquid, and the blanket. And that already includes the reactions, but it still does not include the settling flux. And then, of course, we have this layered 1D clarifier that we're going to be talking about. And the reason is why we're using these variations is the general approach to modeling. I always say to users that you should start as simple as possible, and then you go up when you need to add something. So for example, in a situation where there is denitrification in the sludge blanket, maybe the return will have 2 milligrams less nitrate, and then the whole plant model doesn't fit the real data. And then you can simply add the reactive settler. So you start simple and then you keep going up. And then, of course, how far you can go up. Luckily, we also have the CFD, although this is the computational fluid dynamic models, which also include the flux theory and settling behavior, but account for the flow, the momentum, and in much more detail. They are not, these models, the CFD models, are not, well, I mean, I can't say that they are not widely used, because in the CFD industry, they are used quite widely, I guess. But in process modeling, the complexity is a lot bigger than what we're doing in our models. So it's usually an additional effort to run a CFD model. Now let's go to the next one. And then we're gonna get talking about the model itself. So what you see here is that in a normal clarifier, and sorry, Dave, I forgot your hydro trap here, hydrogravitational trap.
That's okay.
But essentially, there are different solutions to improve settling, not just drop in the MLSS into a settler and then let it settle and forget about it. But we, of course, use flocculation valves, so that promotes the formation of flux. Then we need to remove on the top right, the scum. Some stuff floats up, and if we don't remove it, then it can actually build up to be a big problem, or or have an impact on the effluent. Then on the bottom left picture, you see a baffle that the flow is coming from the bottom right on that picture, and it flows up. And if you don't deflect it, then it will take some solids with it into the effluent. And then there is also lamellar clarifiers. There are lamellar clarifiers. The idea is that it has a lot smaller settling distance than the 2, 3, 4, 5 meter depth that a normal clarifier has. And then the sludge can just slide down. So how do we model these things? The flocculation, well, we can simulate already with a 3-compartment clarifier, or even also the one-dimensional one. Scum is a tricky one. Honestly, there are some approaches. I don't know if Elena has better idea about it. And baffles and lamellar clarifiers really belong to the CFD realm. Okay. And then I also listed a few problems on the next slide, and what can be simulated and what cannot be. Obviously, shallow tanks can be, because the geometry is part of the model. Uneven flow distribution also, so meaning I forgot that this is an animated thing, so I'm not gonna go through all of them one by one. But if you have several clarifiers in parallel, and if you know how the flow is distributed, which is never really exactly equal, then that can be simulated. But all the other parts, all the other impacts, whether something is frozen over, like on the picture on the bottom left, that's that's not something that we normally simulate. The last two is interesting. Bulking sludge when the SVI is pretty high and it's not going to compact at all, and you have 300-400 milligrams milliliters per gram of sludge. That can be simulated by adjusting those parameters that Elena will talk about in the settling model. And then rising sludge when you have denitrification in the clarifier, and the bubbles, nitrogen bubbles, and they float the flux up. That is something that, well, we either take it into account in an empirical way in the flocculant part of the settling equations, or I've seen it also linked directly to the amount of denitrification rate. So the denitrification rate can influence the flocculant settling parameter. All right, I think, Elena, you have some stuff to add to this. Muted.
I was looking for the unmute button. Thank you, Imre. Yes, so in the next part, I will try to talk a little bit about the theory behind sedimentation models. And again, specifically, we will focus in the session on the 1D sedimentation models that are used for secondary settling tanks, because I think those are the ones that we mostly find in commercial simulators and many other software packages. Okay, so as Imre said, if we look at final clarifiers, they can be different, have different geometries. They might have some internal structures as the flocculation wheel and so on. Typically, we start by doing a lot of simplifications to the geometry to actually model them. So instead of looking at all these internal structures, we just look at the shape itself. So we ignore the internal structures. Then we'd have the simple 3D volume. Of course, we don't model in 3D here. We can put this in 2D, then you see this conical shape that a lot of settlers have, so that the sludge can go down to the bottom, and the slope kind of encourages the sludge to go to the center underflow exit. Also, this slope typically we don't consider, so to make it easier, we just make it a big box. There are some more advanced works that do include this changing cross-sectional area to have a bit more realism, but those are more advanced models. Typical models, we just consider it a nice rectangular box. As Imre said, we don't really consider any concentration gradients or different behaviors over the horizontal, over the diameter of the settler. So we consider that everything that's at the same height would behave in the same way. Which brings us to a bit of a 1D model, which actually only takes this whole complex geometry of a clarifier into a very simple geometry, which would only consider how the solid concentration is changing in time and over the depth of the column, without considering any horizontal variations, without considering any internal structures. So this is what we typically use as a geometry in a 1D model. Of course, we consider the volume of the tank here, but we don't consider any horizontal variations. Let's then look at which processes we would include here. So we have several. First, we have at a certain height in our tank, we will have the feed coming in. So the feed coming from our bioreactors. Consider the specific points that this is coming in. Then we have solids that are flowing with the water flow. So we have at the top part of the clarifier, we have an effluent flow rate, so water flowing up towards the effluent weirds. And at the bottom part, we have water flowing down towards the underflow. So these flows up and down are determined by the underflow flow rate, which is usually pumped, and what is left is going over the effluent weir. So this is called convective flow. So just sludge that is moving along with the water flow. On top of this, on top of the water flow and sludge going along with the water, we have our settling flux. So this, of course, is going downwards. It should go down. We want the sludge to settle in the tank. So this is an additional process that we model. So we have the incoming flow, the convection, the sludge flowing with the water, and we have our downward settling flux. Okay, so what we will describe is our solids concentration, X, which is changing with depth and with time. That's what we want our model to do. You see that we actually only consider like a single variable, which is solids, TSS, particulate material. So if you couple this to like a biokinetic model, what you do at the start of your model, at the interface, you will lump all particles or all particulate fractions into this one solid fraction. And for the soluble components, they will just flow with the water. So they will not settle. So that's a little bit how the interface would work with the biokinetic model. Within the settler model, we consider only one variable, which is the solid concentration, which varies over time and over depth of the column. Since it varies over both time and depth, we describe this with a partial differential equation. So if we want to know how our concentration changes with time, we include our different processes in this equation. So we have feed flow coming in. So with a certain flow rate QF, let me just quickly check if I can have a pointer. I don't know. So we have our flow rates, feed flow rates coming in QF at a certain concentration XF. And you see that we used A is the surface area of the clarifier, and then this delta Dirac, it just means that it comes in at a very specific height. So that's that it's a point source into your settler. We add to this, or that we subtract from this, the solid flux, so which is the movement of the sludge throughout the clarifier. This solid flux has two components, one related to convective flow with the water, and one related to settling. The flux, it means how the mass of particles that is moving to a certain surface area of your clarifier. And so this means that if you look at a certain location in your settler, there will be a concentration. And so sludge will either settle or move with the water depending on the certain concentration, and it will move with a certain velocity. So we can describe the flux as a certain velocity times the local concentration, multiplied with the local concentration. So if we split this up, it would look like this. So our flux function has two terms, a convective flux and a settling flux, whereas each flux is a velocity times the local concentration. And you can see that this velocity of the convective flux, it only changes with time. So at the top of the clarifier, this will be, this velocity will be determined by the effluent flow rate. At the bottom of the clarifier, this convective velocity will be determined by the underflow rate. And in our settling flux, we have the same. We have a settling velocity, a velocity of which the particle settles, times the local concentration. Now, this settling velocity function, that's actually the function that is the most tricky part in sedimentation model, because you need to choose which function you use for this. And this is also the one that you need to calibrate in your models. We will talk a little bit more about the settling velocity functions. Imre will talk a little bit on how to choose them and how they were historically developed and how to measure them. But first, we have now our nice partial differential equation that is describing the change of solid concentration over depth and in time. But of course, putting in a partial differential equation into a commercial simulator, coupling this with biokinetic models that are all ordinary differential equations, is not so easy. So what we typically do is we discretize this partial differential equations into a number of, so we discretize our settler into a number of layers. And so we discretize our PDE so that each layer is described by a simple ordinary differential equation. So we get rid of this depth variable in the partial differential equations, and we make ordinary differential equations for each of the layers that describe then just how the solid concentration in that layer changes with time. Typically, in most the models that we use a 10-layer discretization, a very specific low number of discretization, because this adds some kind of numerical diffusion, which causes a bit of smoothing and which dampens discontinuities in the settler. So this is a bit of a sideline. This is why you would see that in a lot of commercial packages and a lot of most of the models we use, we go specifically for this low number of layers for the discretization. So what would our final model then look like? For instance, let's pick our feed layer, layer 6. We can describe the solid concentration X in layer 6 in time by this equation. So first we add our feed flow that is coming in with a certain flow rate and a certain concentration. And you see that now we have here the delta Z, which is just the height of the layer, which helped us to get rid of the partial differential equation. We have in our feed layer, we have water flowing up convectively to the top towards the effluent. So water going out, so solids going out of this layer, moving towards the effluent. We have solids going out of this layer, moving towards the bottom. So dependent on the underflow flow rates. So this is this term. And then of course we have settling out of the layer. We have settling into the layer from the layers above, and we have settling out of the layer towards the layers below. So we have here some kind of settling flux which comes from layer 5 into layer 6, and we have a settling flux that's coming from layer 6 and that's going out into layer 7. We can do this as well for another layer, for layer 4. Here we do not have any feed flow coming in because the feed flow only comes in into one single layer, but we would also have convective flow and settling. In this case, we would have convective flow from water that is coming in from layer 5 and is flowing up. We have convective flow of water that is leaving layer 4 and taking some solids with them. And then we have settling coming in from the top layer, from layer 3 into layer 4, and solids leaving layer 4 through settling towards layer 5. So this is a bit how we model the sedimentation. So it is in theory a PDE, but in most models we discretize this in a limited number of layers, and in each layer we describe it with an ordinary differential equation. So this actually kind of becomes a tanks in series approach almost, except that you have settling working over the over the boundaries of the tanks as well. The tricky part, I already mentioned, is one aspect is the settling flux. So the settling flux we model by a settling velocity function, which we need to determine, we need to choose, and we need to calibrate. And it is multiplied with this the local concentration value. If you look into the discretization, there's an additional challenge that comes. You need to decide in the settling velocity function, which is a function of your concentration. We will see later that typically the settling velocity is a nonlinear function of your concentration. So when you discretize, you need to decide over a layer boundary if your settling will be influenced, or your settling velocity will be defined by the concentration in the top layer, the concentration in the bottom layer. Is it the bottom layer is it the top layer that is driving the sedimentation into the bottom layer, or is it the bottom layer that is constraining what can come in, or is it some kind of balanced in between? So how you define this flux function, so if over this boundary, which concentration you consider is a bit the driving force, that is what we call the flux function. And this has been the topic of some work. I will not go into detail here. I think it's just important to mention that it's not so straightforward to choose this, and that there's been some work done to look into different settling flux functions. Okay, I think Imre will now talk. No, I will still talk, sorry. I will first go a little bit into the theory of the settling behavior. So the settling velocity, what is in there, how does sludge settle? And then I think I will pass the ball back to Imre. Okay. So you would maybe think, practically, it's sedimentation. How complicated can it be? It's solids settling through gravity. But like I mentioned before, it's actually not as simple, because we have the settling velocity will depend on the concentration, and for different sludge concentrations, you might see completely different settling behavior. Typically, we talk about discrete and flocculent settling at very low concentrations, hindered settling at a bit higher concentrations, and compression settling at very high concentrations. So let's look at this in a bit more detail. At very low concentration, you would have discrete settling, where particles settle almost as individuals. They will never completely settle as individuals, but they have a lot of space around them to kind of choose their own path. I like to illustrate this in this way. For instance, look at you being a person on a big square with not a lot of people around. If you want to go from one part of the square to the other, you can do it at your own velocity. You can choose pretty much any path. Yes, there are some obstacles to avoid, so you're not completely independent, but you have a lot of space and freedom around you. So you can walk almost as an individual. That's the idea of discrete settling. Not a lot of interaction with the other particles or humans around you. Hindered settling will happen at more intermediate concentrations, and there's a lot of interaction between particles, which makes that the particles will actually start to settle almost as a single mass. So they will no longer be able to have their individual settling velocities. Doesn't matter if they're faster than the others, they will settle as one mass. You can compare this a bit to a big running event where there's so many people running in the street that it doesn't matter if you are faster than the person next to you or in front of me. There's not really any place to go around them, so you just move with the flow. That's the idea of hindered settling. Compression settling then happens at very high concentrations, where particles more form like a network with a compressive force that is kind of acting against settling. So it will slow down your settling behavior. This you can compare to going to like your favorite band or some kind of rock concert, and you're in the front row. It gets kind of dense there. It gets kind of cozy. So you don't want other people coming in. You don't want to be compacted any further. So what you will do, you will push back against further compaction. That's the idea of compression. Of course, we've talked about concentration, about discrete, hindered, and compression settling that happen as concentration goes from low concentration to high concentration. But it's not only concentration that is impacting settling behavior in a sedimentation tank. Also flocculation, so the state of your flux, are they very particulate or very good dense flux that you've formed with a lot of filaments or not, will have an impact on your sedimentation behavior. So you can see this a bit in this figure where you have on the y-axis concentration going from high to low here. And on the x-axis flocculation state with on the left low flocculant, so particulate flux, and on the right high flocculant. You will see that particulate, and so particulate in the particulate phase on the left, that there you will have discrete settling for much higher concentration, up until much higher concentration. So it will take higher concentrations to reach hindered or even compression settling. Whereas typically, normally in activated sludge, secondary settling tanks, we try to have good flocculated sludge. So we will more be on the right side. And then you see that already at quite low concentrations, hindered settling and compression will occur. And also compression settling will set in earlier. So you can see this a bit, for instance, particulate. One example would be granular sludge, where you have very, very dense granules. They will typically settle more discretely individually than if you go to typical activated sludge, which are flux formed with maybe some filaments. They will be more on the right. Yeah. You see a little picture of what the flux would look like during settling, and you indeed see that they kind of, within hindered settling, settle as a whole downwards in a column. Okay, what does that mean for our settling velocity function in our models? You'll see that typically, like I said, for activated sludge model, we more look at the right side of this figure. So we consider that our sludge is well flocculated. And in the typical concentrations that we find in our sedimentation tank, so the feed flow coming in is typically in this hindered settling region, which is why for traditional settling models, our settling velocity function, the way we define it is more on this right side, and you see that it's mainly focusing on hindered settling. I've let it pass a little bit because, of course, there's ways that we include in these functions to kind of cover compression and cover a little bit also the flocculant settling. I will give it to Imre to talk a little bit more on these settling velocity functions.
Okay, thank you, Elena. Now I understand settling much better than in the last 35 years. Let's go to the next one, where I had an experiment showing, the MLSS in various dilution that you put into a graduated cylinder on the left side, and then you wait a minute, 2 minutes, 4 minutes, and all the way to, maybe 45 minutes in this case. And what you see also is at the beginning, kind of it drops at a constant speed, constant velocity. The blanket or the surface of the sludge is dropping it, and then it's slowing down. So that's plotted on the right side, where there is this linear section, and this is called the initial zone settling velocity. And then you can repeat this experiment with different dilution. So I think that's the next one, is it? Yes, that's the next one. On the left chart, you see these different dilutions. So on the top, it might be, this was an actual experiment, but I don't remember the concentrations. Maybe at the top, it's 10 grams, or the bottom, it's maybe 1.5 grams. And as the concentration increases, the slope of the settling velocity, the surface is getting less and less and less, as you see. And if you plot these measured points as a function of the MLSS of the dilution in that test, then you can get kind of this exponential curve. And what I like, this is an actual measurement. I didn't do the test, honestly. It was somebody else who is obviously very careful, because you see that the points line up with an R squared of 999. I've never seen measured data to line up that one. And I'm fairly sure that she was not, making it up. These were actual measured points in an SBR. And then that's how you get your, this parameter here, hindered parameter, which is sometimes called R-hin, sometimes P-hin, sometimes something else. But that's the way to get the value, the 0.36 there that you see in the exponent, to to use in the settling velocity curve. Okay, what do we have? Next one. This is called the Veselind settling function, and that's because the guy was Arne Veselind. He is right here. Unfortunately, he died 7 years ago, but I still had the chance to talk to him. And it's kind of a good insight into the behavior of the MLSS that he had, and put this Veselind curve on it. Now, then what happened is that I arrived, next slide, please. I arrived to McMaster, Canada in '88. And then Gilles Patry, who was my professor there, he asked me to make a model, and that's how GPSX started. So I put this model, the Veselind model, in the Vitasovic implementation into a language, AXA, Advanced Continuous Simulation Language, and ran the model, and the effluent solids were 10 micrograms. And that's not very usual. It would be pretty clear water. And that's because if you extend the exponential, this Veselind exponential to the left, then you see that it will cross somewhere at the very, very high initial, at a V0 initial settling velocity. So at the top, everything settles pretty quickly. So that's where this idea came, that we should slow it down, and then we ended up with this the orange-shaped curve. There is a little solids in this model, in what we call the double exponential model, or it's called Takacs model, but it's really not used anymore in this form. We added several things to it. That the beginning, there is a non-settleable fraction, so it's a couple of milligrams that will take maybe forever to settle down. Then we have the flocculent zone when you have just a few dozen or a few hundred milligrams of solids, and they are discrete actually, and that's what the reviewers were asking. This is a paper in '91 that we submitted to Water Research, and the reviewers were saying that these are discrete particles, so their settling velocity cannot be connected to the concentration. But then we wrote another paper, which was a little bit beyond me, but Gilles helped with it, which describes that the bigger particles will settle a little bit faster, obviously. So what essentially you end up with in the top of the clarifier is a gradual size selection. So towards the very top, they are the smallest particles, and with lower concentration and a little bit deeper, but still above the blanket, you have the larger particles with somewhat larger concentration. So essentially, there is a link, and that's why this model does work. The double exponential model, we just added this R flock, the second exponential term, which you subtract from the Veselind, and then you end up with this shape. The max ds, that's a range essentially. I think Nam was just commenting in the chat that there is no hinder settling essentially in a real clarifier. So in this range, in this concentration range, the solids is just falling through and hitting this blanket, very fast. So, but if you just subtract the two exponential terms, then you end up here in the middle with quite a high settling velocity, unrealistically high settling velocity. So that's why the function is essentially cut off at this maximum, which might be maybe 200 meters per hour, not per hour, per day. Okay, and then, so I think if we have time at the end, the next slide, please. I have okay, you hit it, so that's okay. There was a one slide saying all the stuff it's hidden, then that's okay. That's fine. There is a whole lot of other things that we probably won't have time to discuss. So then, do we do the simulation example now or at the end? I think I can do it at the end rather. So you can go ahead.
Okay, and that's good. Then I will just quickly touch upon some advancements in sedimentation modeling. So what we are focusing on now, what we're describing here, is indeed the 1D model that is most commonly used. But of course, there has been a wealth of research and development done on sedimentation models to tackle some of the simplifications in the models that we typically use. So I just want to go shortly over a few of those in case you are interested in knowing more, or in case you run into any issues with typical models and you want to look into making them maybe a bit more complex. Like Imre said in the beginning, if the simple model doesn't work for you, these are some topics that may help you add some complexity if you need it. First one, compression settling. So we've talked indeed about what happens at the bottom of the sludge of the sedimentation tank. If sludge starts to accumulate there at high concentrations, that you will have this compression force that will slow down your sedimentation behavior. You can see this in these typical batch sedimentation curves that Imre showed, that normally have this first very linear slope, which can give a measure of the hinder settling, but at some point it starts to slow down the way your blanket height, so your interface, the way it moves down. At some point it starts to slow down, which is an indication indeed of compression settling occurring, which will work against further settling, and so will slow down your total settling behavior. Let's go back to our 1D model where we describe our different processes. So we had feed flow coming in, solids moving with the water, convective flow, settling, in this case, hinder settling going down, that we can describe, for instance, with the double exponential function that Imre just showed. And then if we want to add compression, we have an additional term at high concentrations at the bottom, which is working against the hinder settling velocity. Yeah, remember our rock concepts, where indeed we don't want to be further compacted. What would it mean for our equation is that in our flux function, so we had a convective flux, a settling flux, which we can describe here the velocity with our hindered settling velocity, that we add an additional term for compression with an additional compression function. But what is important about this term and what makes it a bit more complicated, that is you're adding a second order term. So compression does not only depend on the local concentration, but it depends on the concentration gradient. So the bigger the concentration gradient in your sludge bank, for instance, so the bigger the change over height of your concentrations, the stronger your compressive force will be. So this adds a second order term in your differential equation, also in your discretization, which means that it puts constraints on your time constraints that you can use to have a stable solution. So the model becomes numerically a bit more challenging to solve. And of course, instead of only having to choose and calibrate a hindered settling velocity, you now add an additional function, a compressive function, where you also need to choose constitutive functions, so an equation that you want to use to describe compression, and where you also have additional parameters to calibrate. There's been quite some work done on looking into compression settling. How can you describe it? Which kind of functions could be used? How can we calibrate it maybe? I listed a few references. I think especially if you want to look into some nice experimental data, the historical paper of de Klerk et al., Jerifa de Klerk, she did amazing experiments. I just quickly want to talk about it because they're crazy, where she took like a huge batch column that she filled with sludge, and she added a radio tracer to the sludge. And then they went to the university hospital to put it in a big scanner to actually scan the radio tracer, so she could really see how the concentration of sludge was changing over the whole depth of the column in time. Amazing data, which are still available. So I think these are one of the nicest data that I know that have been collected about settling at different concentrations, and she also specifically looked into how compression settling is happening. Second thing I want to talk about is the hindered settling velocity. And specifically, when you go talk about compression, so I think Imre talked about the Visulant exponential function, then about this double exponential function that really, really improves the behavior at low sludge concentrations. There's been many more. There's a lot of power law functions as well. The only thing I want to mention here is that the selection of the hindered settling function becomes more important if you want to add compression settling, because compression works against the hindered settling, so they kind of interact with each other. So the choice of one will impact the other. And the reason I want to mention this is, so here you have some settling velocity data. So here the little crosses are all determined from batch sedimentation experiments. So from the slopes of these batch sedimentation curve, each cross is one slope at a specific concentration. And I fitted different hindered settling functions to them. And you see that all of them fit well our little crosses. Indeed, you have a lot of diversity here in the discrete region or in the low concentration region on which the double exponential function tries to bring an answer. But all of these hindered settling functions actually provide the same, relatively the same fits to our experimental data. However, if you would zoom into higher concentrations, where you compression settling typically occurs, you see that actually relatively they differ quite a lot. So if you want to interested in compression settling, you should not only look into the compression function, you should also take a critical look at your hindered settling function to make sure that this covers well your compression region as well. Again, some work has been done on that. I've looked at it a little bit in our PhD. I know the group of Benedict Plosch has done a lot of work on this. So third one that I quickly want to talk about is flocculation, because of course we've now mainly looked about in our PDE and our sedimentation function, it's all a function of concentration, whereas we know that the flocculation state of sludge plays a role on sedimentation as well. Remember this figure? So indeed, we've seen that the models that we typically use, they only consider one flocculation state, so we will calibrate them. They mainly look at hindered settling with double exponential extensions to cover the low concentration region. We can add compression settling, so we can also cover this bottom region, but it doesn't really consider flocculation. So what will we do if some changes happen in the flocculation state due to shear or something else, for instance? I will show you a little example of, again, a nice batch sedimentation experiment where we took the same sludge sample. We let it settle for half an hour in this case. Then we stirred it at 100 RPM for 10 minutes and we let it settle. And then we stirred it like we really mixed it up very, very, very powerfully. And we let it settle again. And you see indeed that the same sludge sample at a different flocculation state will have a completely different settling behavior. So the flocculation state prior to settling has an influence on the hindered settling velocity, but also on the onset of compression. So what do we do in our models if this happens? Well, in traditional models, we simply recalibrate if we see that our flocculation state has changed. Again, a lot of R&D has happened, so some efforts to create maybe multi-class models where you have multiple classes of particles of different size, so you can kind of cover the flocculation state. Nice in theory, calibration-wise, of course, you add a lot of complexity. People have tried to explicitly add a class of filaments to your sedimentation model to kind of account for filamentous effect on your settling velocity. There's work been done by Nam, who is here, I've seen, to couple EPS or to make the settling parameters a function of EPS, which is then a function of your incoming variability, water quality, your raw wastewater water quality. And there's recently been some work done or being done on hybrid models to compensate for this. Two last slides. Of course, we just talk about solids and settling. There's a huge, sometimes if you have a decent sludge blanket, you might have quite a lot of mass in the settler. So will there not happen any reactions? Will there not be any bioconversion? There might. For instance, denitrification in the settler it's an aspect that might occur. So there have been models developed which are called reactive settler model, where you add in also these biokinetic equations into your settling model. They work if you need this. becomes, of course, very complicated because instead of only one variable, x, you would need to have the full set of ASM variables included into each of your layers of your settler model. So they easily become a bit more complicated. And last thing, of course, mixing and hydraulics. Everything that we talk about today is simplified 1D models. There's been a lot of work done on CFD models for design, how to design your center well, how to put your baffles, so a lot for design. And there's also been some nice work done coupling CFD with flocculation to indeed see a bit how the mixing might impact flocculation and how this then impact your settling models. So a lot of avenues for complexity. I listed here some references just so if you're interested. So there's reading material for at least the whole PhD. I can account to that. Oh, no questions yet. We will go back to our demo.
Yeah, thank you, Elena. Before the demo, can you go back to slide 20 for a moment?
Thank you.
And yeah, I wanted to add something that, being an engineer, time is pretty important for us. And some of these runs, as you mentioned, this one, as
okay.
you mentioned, can be pretty complex and long. The runtime can be pretty long. This would already have, if it's a reactive settler, it would have 10 reactors essentially on top of each other. Each reactor these days have like 100 variables. So that's kind of already, and then it's a very stiff system as well because they pass through pretty quickly, the particles.
Mm-hmm.
So that's one reason why, I'm familiar with the mechanistic modeling of the compression part. But we're essentially, I have to admit, we're using an empirical way of doing it. It's essentially just slowing down the hindered settling velocity, which is what the compression function would do, but it's just using a third exponential. So it's essentially now it's a triple exponential equation that I guess most of these commercial packages use. The other thing that I wanted to point out that we have layer 6 here, and the input, the MLSS is coming in, and then it splits immediately. You had one slide which was even better, I think, than this, which splits immediately up and down for a flow up and down. So what that would mean is that this model doesn't wash solids out until the blanket gets into the feed layer. So for that one, we developed another empirical method, essentially depending on the flow, the surface hydraulic loading, we can reduce this feed layer. So it gets deeper and deeper when you increase the flow, and then it will push solids up. So I know it's not very scientific, but that's what's being used. It's being used, in the commercial packages. Okay, so then
good point indeed that this feed layer, I now put it in layer 6, but that this is indeed a choice, and there's indeed models that exist that make this dynamic where the position of feed layer
or even split it into several, as this shows. Yeah, this is a drawing I made like in 1990. Scary. So I will share my screen.
Share your screen? Okay, I will stop sharing.
And then we go screen 1. And then let's move this out of the way. And you should see a little village, actually. Yes? Okay, good. And then, so I tried, so what the idea here is in the remaining 5 minutes or 10 minutes is to show you how this looks in a simulator. I only have access now to the Sumo simulator. So I wanted to look at a real example, and then it turned out to be too complex. So I'm not able to run it here. But the point here is that there are the data points, the measured data points of the return activated sludge, so the RAS concentration, and the yellow one is the model. And what happened here, we don't know. But what we know actually is that when data points and the model don't match, then you can have two problems. You see at the back end here, there starts to be 1,000 milligrams or 1,500 milligrams of difference. And what the model does, it absolutely keeps mass balance all the time. And I don't think that the sensors do that all the time. So there is sensor drift, of course, and they need cleaning. So if the MLSS is right, which I don't know in this case, but if it's right, then these solids that the model predicts, it has to go somewhere. It cannot go to the effluent. The effluent is really low. You see, it doesn't show up on the scale. So the point is that you always have to think about in a mass balance, maintaining the continuity. So instead of this, because it's a slower running real case, I will play a little bit with a very simple model, which is just actually it's a hydraulic SRT example from Sumo. And what I did is I went and changed the clarifier, which was initially, it was just a volumeless point separator. I changed it to a layered flux model. As I mentioned, there are 3 versions of the clarifier model. So now it's layered flux model. We're using actually 9 layers, and that's coming from the fitting of the numerical diffusion that Elena was talking about. That worked better with 9 than with 10. So it's unfortunately it's case specific. Otherwise, you would have to introduce a kind of a back mixing between the layers to describe this better, which will slow down the simulation even more and add another parameter. So that's another option. But this 9 layers, what can it do? We go to the simulate tab, and I mean, if I just run a 1-day simulation, then the flow pattern is that simulated diurnal flow pattern. So goes up around 2 p.m. or something and goes down at midnight or 4 a.m. And then that is reflected in the settling in the solids curve. Obviously, this is between 10 and maybe 19 milligrams or so. It's so it responds to the hydraulic loading. This is the second part, so the flocculation part of the settling curve. What I'm showing, I can also show the other piece, which is the MLSS and the RAS. And obviously, when during the night we slow down the flow, then there is a build up in the CSTR and a drop in the RAS, so in the blanket. There's also a blanket somewhere here, but it's a little bit too small number. So that's what the blanket does, it dropping down during the night. Now, if I want to show some dynamic run here, then I could change the RAS flow, so the return flow here, by maybe simulating an equipment failure or a maintenance issue. So maybe they have to, this actually happened in Toronto, that they had to replace the RAS pumps and they had to shut down the clarifier return for some time. And the question was at that point, how long do we have before there is a problem? So that's something you can simulate. We can maybe, I don't know how long this is going to be, but we put 10 days in and start running. And oh, it's too fast. So let me stop it and then go to a much slower run. And right now we're returning about 100% of this influent flow. So now we have our failure. And what happens is that the blanket is building up. Here is also the profile. let me stop because it's going too fast. What you see to explain the profile, this on the right side is the bottom of the clarifier. So that's the RAS concentration, 1.4 grams. 14 grams, sorry, 14 grams. And then the 9 layers to the left, where this is the effluent solids. So the effluent solids at the moment is, we can better see it in the effluent solids. So let's take the big numbers off. And that's what the effluent is doing. It's already feeling that there is an increase in the blanket, but it's not a washout yet. Because in a washout situation, you will lose hundreds of milligrams in the clarifier. So if I turn this back, we repaired our RAS pump and continue. Then the blanket will fall down back to where it should be or where it was, maybe maybe a meter high, 3 feet or so. And the solids concentration effluent came back. The RAS, where is the RAS? Here. There was no RAS, return concentration during well, this was like a 2 and a 3 day breakdown, so it's pretty serious. That will depend a lot on the loading of this clarifier. In our examples, this is just a standard example that I pulled up, and it's over designed because we're demonstrating normal operation. So essentially, it's emptied, the clarifier emptied down, it's getting back to the normal return concentration, and effluent solids and blanket also recovered. Let me see. The blanket and the effluent solids. This is not the effluent solids, this is the CSTR. Effluent solids is here. So you see, as soon as we started returning solids, started to drain the clarifier, then and the effluent solids drop down to the normal level. And the point here is for the question in the chat is that the settling parameters, there are different correlations for the SVI, so you could put in an SVI as well, but the Vaseline settling velocity, the V naught is this number, the hindered settling velocity is this number, and that flocculant settling velocity or parameter which is also an exponential, that's the value of it. And then we have a coefficient for compression which starts around 6,000 milligrams in this specific implementation. And here are the minimum fraction of non-settlable solids. So if you have 3,000 milligrams of ABLSS coming in, then you will end up with 3 milligrams, I guess, that won't settle, or with 20, it's always taking the smaller of the two. So that kind of shows you a very simple example, and I guess it's time for questions.
There are already some questions in the chat. Some are already answered, but let me check. I can maybe read out the ones that are not answered yet. So we have a question of Nam asking, I am not sure if we can see hindered settling regime for in the clarifier. It just happened quickly, and then compression settling regime is in the true clarifier. Do you have any comments or responses to that question?
I think that's a theoretical question for Elena.
Yeah, sorry, I was looking for the unmute button again. And I guess it would be nice to have like a lot of. It's true that there's not so much data that is being gathered from really settling inside a real sedimentation tank. You have a bit of a echo, but indeed, of course, the way we model it is you have the feed flow coming in, which is at a concentration where you would expect hinder settling. But then, of course, if the sludge blanket is not there, then there might be some dilution happening. So it kind of depends on what the final concentration is and where your sludge blanket is as well. Dave, you clearly want to say something. Please go ahead.
Well, can you hear me?
Yes.
I was trying to be polite and look for a raised hand thing, but I don't see it on this one. So it goes back in my mind, and it's never been published, somebody saying hindered settling does not occur in a secondary clarifier. But I've been saying it for a few years, and I think it's all there in the literature if you just read it. You have to start with the force balance. And the particles begin, as they come in, they get diluted, and they're in type 2 settling. And then you need another, and the force balance is there. It's not Stokes' law. Stokes' law doesn't work in a clarifier because the particles are the right size, only a small number of them. Go back to Stokes and do all the math, and you'll find that Stokean doesn't, it's modifications of Stokes' law that include the inertial term. But what happens is these particles are settling by themselves, right? And the forces are balanced, the same as when you jump out of an airplane and you reach a terminal velocity. In order to change those velocities, you need another force. The forces are balanced. The only other possible force in a clarifier is the compressive force from the floor. So there's no way to transition with the force balance from a type 2 discrete Stokesian, you can call it, but it's really not Stokes. It's the force balance. And there's no way to add another force to transition into hindered settling, right? It has to transition when that compressive force rises from the floor, and that takes you right into compressive settling. So you drop like snowflakes, and then you hit the wall. And that takes me to my second point is compression settling was my PhD. But I don't see why we're allowing it to occur in a secondary clarifier. The thickening initially to the first point, when you first hit the top of that blanket, you transition from maybe 300 milligrams per liter right into 10,000 milligrams per liter. That 10,000 milligrams per liter normally exceeds the mass balance of a typical clarifier. Typical mass balance is 2,500 in, 7,500 out the bottom, a RAS rate of 3. So you initially, as soon as you hit that blanket, you get to 10,000. What happens, you overcompress in the compressive blanket to maybe 15,000 milligrams per liter, 15 grams per liter. And then what do you do when you get it back to the underflow, transported, in order to meet that mass balance? How do you meet the mass balance? Anyone? You have to dilute it back, right? Your mass balance around that clarifier has to be 7,500 coming out. But as soon as you hit that blanket, you concentrate to 10,000, and then you wait 2 hours for this compressive settling to occur. And then you bring out of the clarifier, you need it back at 7,500. This is time averaged. And the only way you can get there is by diluting. That's that kind of theory of rat holing, but it occurs due to the mass balance, not due to the lack of transported solids. So my conclusion is, in all of this, that hindered settling doesn't occur. Compressive settling, I don't know why we're modeling it, because we shouldn't be in the clarifier for the amount of times that these things happen out at 3-4 hours. We should be out of the clarifier as soon as we achieve that underflow concentration. And what you need in order to accomplish that is more surface area, but not really more surface area. You need to provide more surface area in the same volume. And it's completely unfair in some ways with academic, because I haven't written a thing in 20 years, or since 1991 when I first saw that image of Imre's, I was like, well, I don't know about this. But it's taken 35 years to get there. At least I can explain it. I need to write it. It's not fair to just ambush people, but I kind of enjoy it. Thank you.
I knew that we were going to get this one.
Yeah, well, my point is a lot of it doesn't make sense with the theory, but we continue to operate based on these techniques that were developed quite some time ago that you know, my approach has been for the last couple of years that the theory doesn't resolve itself, that many of the techniques we use don't make sense, that it's hard to get the techniques to go with the data very well. I mean, you read that IWASDR6 and it says don't use flux theory. Don't use these equations to design a clarifier. But we all say, well, we ignore it. You read on SVI. SVI is not a good parameter. We all just keep doing it. You know, my conclusion has been to throw out the entire design and start with a design that makes more sense. But that's for another time. So
You need another PhD for that.
yeah,
Yeah. But did you get
that's
the
the
first
problem.
one? That's yeah. So I give you that it's what we're doing is obviously simplified. What you're saying is also simplified, because there is the collection system, and it's a much more complex thing than just something hitting the blanket.
Yeah, I mean, I spent more than 20 years working on all these techniques to try and simulate what I feel now is left over from the mineral industry. The first clarifiers were in the mineral industry in the 1800s, and we've kept the physical configuration and try to model our way around it to give us results that make some sense. But then the people that I really admire in the business, Hazen, Camp, the Gordon Culp papers of the late 60s, and the Vestlin paper that said don't use SVI, these are the ones that made the most sense to me. But we tend to just put them on the side because it oftentimes, I mean, we have a lot of SVI data out there. Nobody wants to just throw it out, but it's been advised that it does not work well scientifically. My approach is to throw the whole thing out and start with a new configuration.
Yeah.
You know?
So everybody, we need also independent thinkers, and that's why I like Dave very much. But we also need them talk a little bit less.
Yeah. That's I'll go away again for a couple of years.
So that other people can have some questions.
I think these are all very nice points, and I think indeed something that the idea of the MIA Academy is to go to the basics of what the models that we're using now, of course, but I think it's important indeed to bring into the session that these models that we are using that are there in commercial simulators, for sure, they're not perfect. So
let me also say, I think these are research models, because when it comes to clarifier design in the real world, I mean, I did it for 30 years, and we never applied these techniques to, I would say, the vast number of clarifiers that are ever designed by people that don't know these groups exist. But also, even at the larger consulting scale, the consultants that are there are not regularly, and very often not at all, applying these models when they design clarifiers. It's 600 gallons per day per square foot, and when it comes to the depth, it may as well be a dart.
But of course, if you're looking into more like flow sheet modeling, commercial simulators, these are the models you will find, and I think that's why. This is what
I would also say, just because they're in the simulator doesn't mean they're being applied, at least in the United States. I haven't worked on clarifier designs in Europe, so yeah.
Somebody else?
Yeah, I think all of the questions in the chat are answered. If anybody has any other questions, you can still put it there. Otherwise, I would like to thank Elena and Imre for the very clear explanation on sedimentation models. And then I would just like to show this. Oh, I don't know if you can see. It's a little spoiler of our next session. Our next session will be on physical-chemical modeling, and we will have Helene and Kimberly presenting in it. It will be hosted on February the 3rd at 3 p.m. And the registration link will be online on LinkedIn very soon. I see there. is still some things in the chat.
Further questions, I mean, feel free to reach out by email as well after the session.
There is a question on discrete particles, if using double exponential is possible or not.
Yeah. So I think, I think there's a disconnect between the science and the practice. So obviously, when you have a mixture of particles that are not touching each other, but they have different sizes, so there's a size distribution, then they will drop at different rates. And that's the Stokes equation, and you can calculate the individual settling velocities. And in a clarifier, they will be kind of sorted into ranges, right? At the top, you have the tiny ones that couldn't resist floating up, and at the bottom, you have the bigger ones that kind of went a lot slower up. And more bigger particles will mean more concentration, and that's why the double exponential to me works. There's also a paper. If somebody wants it, please write to me, imre@dynamita.com, or find it it's on many places. But it explains this in a mathematical way, why that equation is valid.
Design a clarifier for a settling velocity distribution of discrete particles.
We're talking about primary sedimentation.
Like primary or grit removal, right?
Yep, yeah.
The only particle you're really worried about is the particle with the lowest settling velocity, because you're going to split the particle size distribution right along that settling velocity. The particles are either going to go up or they're going to go down. And we don't care what distance they have to travel to go down. That was Hazen's original 1904 paper. And we really don't care how long it takes for them to get to the removal device in the bottom. So what you're left with, and really the whole design is based on what is the lowest settling velocity particle you want to remove, and providing enough surface area for that particle. You're going to have a constant concentration of each class going up and going down. And
No.
Yes, we went over this at DC years ago.
Yes. Yes, because there is the particle that is like half a micron, and there's the particle that 10 microns.
Right.
And they will, if you design for the half a micron, then you're gonna have a very, very big clarifier.
And there's experimental evidence that bigger particles or smaller particles, they don't have the same fractionation when it comes to organics and inorganics. So of course, which particles play in your fractionation as well?
Well, I'm just talking about the physical chemical here, not adding the biological portion onto there, of course. It's not the size of the particles, it's the settling velocity that matters.
Right.
Of course.
Yeah.
Because the clarifier works on the settling velocity, it doesn't work on the size.
Of course.
Yeah.
I think there's some discussion in the chat on like the particle settling velocity distribution and the work that is done there. But can I propose that we move this more technical discussion to another time?
Mm-hmm.
Maybe
good idea.
Wrap up the more MIA Academy session for now.
Yes, I see there's no more questions, so I think we can end this session here. Thank you very much for joining.
Thank you, Luz,
for organizing. Managed to overwhelm them. Okay.
Thanks for adding to the discussion, Dave. Very good people here.
I appreciate all the work. It's just that's we go and measure settling velocity distributions, but the way I see it is it's only the smallest particle that matters, you know.
Nice
All
thoughts.
right. Bye, guys. Bye-bye.
Bye-bye.